Good morning, everyone. Welcome to the GPDP training on Basic and Advanced LNG. I am Angelou Pagopo of the Gas Policy Development Project. This training is co-organized with the Department of Energy, the Commercial Law Development Program, or CLDP, of the U.S. Department of Commerce, USAID Asia Gas Partnership, U.S. Energy Association, and Gas Technology Institute. Of course, this training wouldn't be possible without the support of our funder, U.S. Department of State. We have a two-part training. We will have the basic LNG course today and the advanced LNG course tomorrow. These will be presented by our esteemed expert from AJS Consulting and Advisement LLC. Before we start the program, may we request Dr. Rizalinda De Leon, Project Director of GPDP, to deliver her welcome remarks. Dr. De Leon.
Thank you, Angelou. Good morning, Ms. Kirsten Madler from USAID Washington, D.C., and all participants today. A very pleasant morning, and of course, good evening to our friends in the U.S. It's my honor to welcome all of you to our two-part training on basic and advanced LNG. We are already at our fourth and fifth courses in the series of trainings, and we are glad that you are joining us once again. During our two-day session, we will learn the characteristics of LNG that influence design and material selection, as well as LNG fuel system components, equipment installations, operation, and decommissioning. Our courses will be discussed by our esteemed resource speaker, Mr. Anthony Scaraji of AJS Consulting and Advisement. We thank Mr. Scaraji for taking time out of his busy schedule to impart valuable knowledge and expertise on the natural gas industry. This two-day training was made possible with the help of our various U.S. partners. Thank you to USAID's Asia Gas Partnership, Commercial Law Development Program of U.S. Department of Commerce, United States Energy Association, and the Gas Technology Institute. Special thanks to Ms. Sarah Blanford and Mr. Kexin Liu for closely coordinating with our team to iron out the details of the training. Of course, we would also like to thank the U.S. Department of State, which is GPDP's funder, without which this series of trainings would not have been possible. Thank all our participants from various Philippine government agencies for being with us today. We are inspired by your enthusiasm and continuous dedication to learn more about natural gas. We hope that this two-day training will provide you with firmer understanding of the LNG industry. So may everyone have a productive and worthwhile time during our training. Thank you all once again and good morning. Angelou, back to you.
Thank you very much, Dr. De Leon, for that wonderful message. Now to give her remarks is Ms. Kristen Madler. Ms. Madler is the Clean Energy Coordinator at the Center for Environment, Energy and Infrastructure of the Bureau for Development, Democracy and Innovation in USAID, Washington, D.C. She manages USAID's Global Energy Utility Partnership Program, which provides targeted workforce development between the U.S. and developing country utilities to share best practices on topics such as the integration of variable renewable energy and utility modernization. She co-manages USAID's Scaling Up Renewable Energy Program, focused on strategic energy planning and the competitive procurement of clean energy. Ms. Madler earned a master's in International Business Administration from IADA in Barcelona, Spain. Please welcome Ms. Kristen Madler.
Thank you, Angelou, for the kind introduction. Hello, everyone, and welcome to the beginning of this exciting training program. And as Angelou mentioned, today's webinar is co-organized by the U.S.-Asia Gas Partnership. And so this is a public-private partnership between government and industry representatives to optimize the development of secure, reliable, and economic sources of natural gas across the Indo-Pacific. And for those of you who are not familiar with the program, this partnership includes a series of both live and recorded webinars featuring leading US and international gas sector experts, which are hosted by our partners, the US Energy Association and the National Association of Regulatory Utility Commissioners. So if you haven't done so already, please register for upcoming webinars or listen to any pre-recorded webinars in the series at usca.org. And the Asia Gas Partnership, the Department of Commerce Commercial Law Development Program, and the State Department collaborated last year to deliver a case study to highlight lessons from the Philippine Downstream Natural Gas Industry Investors Guide, which that webinar may be of interest to this group. And so you can also find that at usca.org. And today we look forward to hearing from our speaker about LNG basics, plant components, the design and considerations for LNG facilities, commissioning and operations. And as the power sector charts various pathways toward decarbonization, this flexibility and diversification in the system are imperative to enhance resiliency. So natural gas coupled with renewable generation offers energy security benefits and could also support the Philippines in achieving national goals to develop the country's power sector. And together, natural gas and renewables can help to contribute to a low carbon and reliable electric grid and affordable service by diversifying the generation mix and hedging risk associated with market and policy uncertainties. And some of the factors driving the transition toward these synergistic portfolios of natural gas and renewables include price stability, policy incentives, regulatory reforms, flattening demand, advances in technology, and innovative business models and financing mechanisms. So in closing, I would like to thank you all again for joining us today. I look forward to seeing you virtually in other upcoming Asia Gas Partnership webinar sessions. I would like to thank our presenter, Anthony Scaraji, for carving out time to share your perspective with us here today, and also like to thank everyone who worked behind the scenes to nail out the details for this training program. We greatly appreciate all of your time and your commitment to these efforts. Thank you so much.
Thank you, Ms. Madler. So before we move on to our first topic, we wish to acknowledge the following agencies with us today: Department of Energy, DILG Bureau of Fire Protection, DENR Environmental Management Bureau, Department of Labor and Employment, DOH Batangas City Health Office, Batangas City Engineers Office, Philippine Ports Authority, Marina, Philippine Coast Guard, Senate Committee on Energy, and House Committee on Energy. Thank you very much for being with us today. Finally, just some quick reminders to all our participants. If you have any questions to our resource speakers, you may post a question in our chat box. We will be reading your questions during our Q&A session after the presentation. Alternatively, you may also take note of your question and press the raise hand icon during the Q&A session so we can call on you and you can ask your question directly. Lastly, we will be preparing certificates of attendance for the participants of today's training. Kindly make sure that you answer the attendance form so we will have your complete details. A link to the attendance form is posted in the chat box. Now, let's proceed to today's presentation on basic LNG. This will be presented by Mr. Anthony Scaraji. Mr. Scaraji is the principal for AJS Consulting and Advisement LLC, where he has supported various efforts, including large-scale LNG liquefaction development, LNG facility regulatory inspection and post-inspection compliance, evaluation of industry standards and regulations, evaluation of assets for potential investment by private equity, and first responder LNG training. He is also a principal member of the National Fire Protection Association standard for the production, storage, and handling of liquefied and natural gas. Mr. Skaraji is a member of the American Institute of Chemical Engineers, former director of the Northeast Gas Association, and former member of the AGA Supplemental Gas Committee. He has supported USDOT PHMSA in evaluating a request for proposal responses. He holds a BE and ME in chemical engineering and an MBA in finance and investment. Ladies and gentlemen, Mr. Anthony Skaraji.
Hello, everyone. Thank you very much for having me. This is a pleasure to be able to deliver this this presentation, Basics of LNG, to the group. Thank you very much for the opportunity, and I'm very happy to share any knowledge I have. Normally, when I do presentations, I like to collect questions while things happen. While I'm presenting something. That way, those kind of questions tend to drive the discussion a little better, and really get to the core of what people are really interested in. So, if you'd like to, I'm open to that. I'm open to taking questions as we go along. I'm also open to the standard presentation methods where you wait till the very end. So, whatever you'd like to do, we can do it that way. Okay. And I assume I'm sharing my screen. Is that how that works?
There's no, we can't see anything yet, Mr. Skaraji.
Right. Okay. Yep. I'm right. I was flashback. Do you see my screen?
There you go. Yes.
Okay. So once again, thank you, everybody. And we're going to go through, there's a lot in this presentation. There's a lot to explain, a lot to discuss. I may move kind of quickly, just in the interest of time, but that doesn't mean that you can't stop me and ask a question. So just moving right along. Brief history of LNG. We're going to talk about, the basics in LNG, a brief history of LNG, what LNG is, properties of LNG, how it's made, things like regasification, what the major components are in an LNG facility, and design considerations for LNG facilities. So that's the outline of, excuse me, of what we should be covering today. Okay, brief history of LNG. I'm sure many of you heard of Michael Faraday. He invented a ton of things. One of the things he did, he was the first person to liquefy natural gas back in 1823. During the time in history when there was a huge scientific boom, and one of the impetuses at the time was to see what you can do with gases, what kind of gases you can turn into a liquid. And as I said, Michael Faraday was the first person to try that with LNG. So just very, very briefly, people don't think of him when it comes to things like that. He's usually thought of with electricity, right? So that's interesting. First LNG plant was actually built in the United States for the United States government, right, in Fort Worth, Texas. It had no storage. It was built to actually extract helium from natural gas to aid the World War I war effort. So LNG was, I guess you can say, was a byproduct of helium production. So that's another interesting tidbit. There was first LNG ship, first LNG by ship. A company called Comstock was developed. ConocoPhillips and Union Stockyard. Later, Shell joined the mix. They converted a regular cargo ship to transport LNG. It was called the Methane Pioneer, and it was a 5,000 cubic meter ship. And its first LNG was produced in Louisiana in the United States and shipped to the United Kingdom. So the very first cargoes, people did not think in the old days of the United States as an LNG exporter, right? These days, it's very, very different. But the initial shipment of LNG by ship was actually from the United States, which is pretty interesting from a historical perspective. First commercial LNG facility was built in the United States in East Ohio at the East Ohio Gas Company, built in Cleveland in 1941, and we learned a lot of lessons from that particular facility, because it actually turned out to be one of the largest disasters occurred at that facility at LNG, which really taught the industry lots and lots of lessons, and we have a very, very safe industry now. So first baseload LNG export facility was in Algeria, 1964. 65 when it was commissioned, then it was actually in service up until around 2003. So was a very, very productive plant, and it used the original facility used a unique design where it actually stuck LNG into the ground and froze the ground, and that was the tanking system that was used to store the LNG. That's not done these days because it's not very efficient, but that was a unique application back in those days. So that's the real basics, very basics of LNG history. So what is LNG really, right? LNG really is nothing more than natural gas that's been cooled down and turned into a liquid. Natural gas, has many components. It has methane. The simplest hydrocarbon is methane, right? Which is one carbon atom, 4 hydrogen atoms. Natural gas is made up predominantly of methane. It contains ethane, propane, butane, pentane, hexane, and many other things. When you talk about natural gas and you talk about the components in natural gas, when you discuss lighter end components and heavier end components, generally you're talking about basically the molecule size. So CH4 would be the lightest component on my list here. Hexane, C6H14 would be the largest component. And if you look down at the right column there, I guess you can see my cursor here. In this column here, you see C6 plus. When you talk the natural gas industry, components over C6 generally are a very, very small component of the whole natural gas stream, and they tend to lump them together. So C6 pluses means any molecule of C6 and higher. Okay. What is LNG? What are its properties? Well, when you talk about LNG, and even when you talk about natural gas, one of the kind of tripping points is that all natural gas is not the same. So therefore, all LNG is not the same, because LNG is derived from natural gas. So when you talk about the properties of LNG, and somebody might say that the temperature of liquefied natural gas at about 1 or 2 psi as a liquid is minus 260 degrees Fahrenheit. Somebody else might say minus 258 degrees Fahrenheit. Somebody might even say lower numbers than that or higher numbers than that. It's not because one person is more correct and one person is less correct. It really depends on the composition in that LNG. So in that natural gas that will derive from those, you'll derive the specific properties. So anytime you hear about a property in natural gas or a property in LNG, and you hear somebody talk about minus 260 or minus 160 as to when vapors are lighter than air, just remember that. Just because somebody else uses a slightly different number, it doesn't mean one person is right and one person is wrong. Oh, well, down here, an important point down here is that LNG, as it sits in storage, the composition of LNG will actually change over time, and that's because as it sits in storage, it's slowly boiling away. And as it's boiling away, the lighter end components within that LNG are predominantly boiling off, or predominantly turning to a vapor, which means you're concentrating the LNG in that tank to the higher end, to the heavier hydrocarbons. So over time, the composition of the LNG changes and all of its properties will change within a tank. So the longer it's maintained in storage, the higher the heating value of that LNG raises to, and it'll actually warm up in temperature. But just something to keep in mind. So properties of LNG. Really what LNG is natural gas in its liquid state, mostly methane. It does contain ethane, propane, and sometimes traces of other components like butane, right? As you get higher in the hydrocarbon number of carbons in a hydrocarbon, those components will tend to be gas at lower temperature, at higher temperatures. So, for example, if you had pure propane, right? You know that people use propane all over the place, and propane is not a refrigerated liquid. It's just it's a gas stored under pressure, and you have both liquid and vapor. So the different components within natural gas mixed together are what give it its properties, as I said before. When I showed you the previous slide, I showed you that you had methane, ethane, propane, butane, all the way up to hexane 6+, but you don't have all those components in liquefied natural gas, because as you make LNG, those heavier components will actually turn to liquid sooner and will be extracted from the process, because if they're not, they will actually freeze up in the equipment before you actually turn the methane into LNG, right? So even though you have natural gas with products up to C6 in them, you won't get that in your LNG. So LNG is not stored at pressure. It's stored just above atmospheric pressure, and at that pressure, LNG will remain at about minus 260 degrees. So you can think of that as you would a pot of boiling water, right? So just like water on a stove that's heated up to a point where it starts to boil, remains at its boiling temperature until all the water is gone. Well, LNG boils at minus 260 degrees at about atmospheric pressure, and will remain at about minus 260 degrees while it's boiling away. So when you store LNG, there's no active refrigeration that takes place. There's just this boiling effect, which the industry calls auto refrigeration. So while it's sitting there boiling away, it's maintaining its temperature at 260 degrees. You can think of it as the heat that is being transferred into the LNG is enough heat is being used to actually take a small portion of that LNG and turning it into a vapor and vaporizing that small bit of LNG. So all that heat that was absorbed went into making that bubble, right? And the rest of the heat, the rest of the LNG remains at its saturation temperature and pressure. LNG is clear, odorless liquid with a density about half that of water. So, that means it will float on water if it's spilled. So what are the properties of LNG? It's a cryogenic liquid, minus 250 degrees Fahrenheit. And as such, it requires special handling, right? Those are cryogenic temperatures of very, very cold temperatures. When you liquefy natural gas, the reason you do that is because you gain a benefit, and that benefit is that you reduce the volume of that natural gas by about 600 to 1. So you can think about a glass of water, right? You can have one glass of water or 600 glasses of water. 600 glasses of water take up a lot more space. So when you're trying to store natural gas, if you store it as LNG, you can take up a lot less space. It's very, very, very economic that way. It also lends itself much easier to transportation across great distances. So LNG is not flammable and not explosive, right? That's important. People don't, not everybody understands that LNG itself is not flammable. The vapors that are liberated from the LNG are flammable. Those vapors are just like natural gas vapors. Natural gas vapors are only flammable in the range of 5 to 15%. And in unconfined areas, natural gas will not cause an explosion, right? So you have the same exact properties with LNG once it turns back into a gas as you do with natural gas. Okay, when LNG spills, now this is a unique thing to LNG. Natural gas is lighter than air, right? I think most people know that. So when you have a natural gas leak, there is no worry in an unconfined area because that gas will dissipate. It will raise into the atmosphere and dissipate. LNG, because it's very, very cold, when it first vaporizes, when the cold LNG is released and first turns back into a gas, those vapors are also very, very cold. Just like I mentioned before, as a pot of boiling water stays at its boiling point until it's all gone, until it's all turned to vapor. The same with LNG. So when you first spill that LNG, the vapors that come off that spill are going to be at minus 260 degrees Fahrenheit. Well, natural gas vapors at 160 degrees Fahrenheit or colder are heavier than air, right? So I think most people understand that cold gases are heavier than light gases. So, cold air falls, hot air rises, right? Same is true for any gas. So at minus 160 degrees Fahrenheit is about when the vapors of LNG become neutrally buoyant. So if you did have a spill of LNG, that LNG vapor would remain close to the ground until it reaches about 160 degrees Fahrenheit, warms up to 160 degrees Fahrenheit. At that point, it would then dissipate and act just like natural gas. And keep in mind, if you have heavy vapors and you're in a confined area, those vapors can actually displace oxygen, right? So it can cause asphyxiation if you're in a confined area. Okay. So why LNG? So we talked about this a little bit before. Arguably, the best reason for converting natural gas to LNG is because of the huge volumetric efficiencies you get in storage. So I have on the screen here an overhead view of an LNG facility in the United States, and it has these two tanks here. And just imagine you would need 1,200 tanks of natural gas in its gaseous state to hold the same amount of natural gas these two tanks hold in the liquid state. So imagine the footprint you would need to have for something like that. It goes way, way off this particular map here on the screen, right? And those volumetric efficiencies allow natural gas to be efficiently transported over long distances. The other major benefit to natural gas, to LNG, is that because you can hold so much volume in such a small place, a facility like this that may not have access to large pipelines, or may, in some cases, not in this case, but in some cases, may not have access to any pipelines, can still support a local grid system on natural gas, right? So it's an available energy source, even in areas where traditional it brings in an energy source to areas of reliable energy source to areas where pipelines might not exist now, but may exist in the future, right? So you can build the natural gas infrastructure in a region, service that with liquefied natural gas, and then over time build a pipeline system into that area. So what makes LNG special? Well, one of the best parts as a chemical engineer, I can tell you one of the best parts is it's easy, right? It's totally a thermodynamic process. There's no chemical process that takes place. If you have an air conditioner and you understand how an air conditioner works, it's basically the same idea for taking natural gas and cooling it down, except that you cool it down much colder than you do air in HVAC systems. You cool it down enough so that you can turn the natural gas into a liquid, and that's that minus 260 degrees Fahrenheit. As a liquid, being minus 260 degrees, the materials that you use that are required in an LNG facility or in LNG applications are very, very unique, right? As things get cold, they tend to get brittle. Brittle things tend to fracture, tend to be susceptible to shock and fracture as a result of that shock. So the materials that are used in LNG applications have to remain ductile at these very, very low temperatures. The other special consideration is that, you know, the capabilities of materials at cryogenic applications have to actually be investigated and you know, in a laboratory and determined. You cannot extrapolate, you know, data to get the to determine how a material will react at those cryogenic temperatures. Making liquid. So what it takes to actually take natural gas and turn it into LNG, there are two broad steps. One is gas pretreatment, and the second step is actual liquefaction, right? So we talked about natural gas containing many, many components. Well, when it's pulled out of the ground, you know, I said it has natural gas contains methane, ethane, propane, butane, and you know, heavier hydrocarbons. Well, that's actually after that natural gas gets processed somewhat to clean it up a bit, right? So if you don't take all those items out before putting it in a pipeline and then using that pipeline gas to become LNG, you have to take all that stuff out plus more before you can actually take that natural gas stream and turn it into a liquid, right? And so, you know, in a natural gas in a natural gas field, you'll have, you know, nitrogen, ethane, butane, you know, heavies. You'll have compressor oils, right? Because in those wells, to extract the gas from those wells, you have compressors, you have equipment that you run. So there's compressor oil, there's hydrogen sulfide, which is a poisonous gas. There's water in that natural gas, as well as the other items that we talked about already. You have carbon dioxide. Sometimes you have carbon monoxide. You've got all kinds of dust. You've got all kinds of stuff that is naturally occurring in natural gas. So in order to turn that into liquefied natural gas, you got to get rid of all the stuff that's going to screw you up, right? When you try to process this, if you were to take water, for example, you see water as a component in here. Everybody knows that water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. Well, you're trying to cool things down to minus 260 degrees. So someplace in your equipment, if you have water, it's going to freeze out, right? And when it freezes out, it's going to slowly block up flow through your equipment, and you're not going to be able to make any more LNG. You'll have no more flow through your equipment. But that's not just true for water. That's true for the compressor oils. That's true for heavies. That's true for CO2. That's true for many, many components that are naturally occurring in natural gas. So they have to be removed. Otherwise, you will not be able to have an effective production of liquefied natural gas, right? So when you get done with your pretreatment, hopefully, if everything is going well, you wind up with a tiny, tiny bit of nitrogen, methane, ethane, and propane, and maybe a little butane, right? So pretreatment gets you from this to this. So why does the composition have to be different? Well, I just gave you the preview on that, right? Components will freeze out, foul your equipment. You won't be able to make your LNG. You'll wind up having a lot of downtime in your plant. And so these are the things that are typically removed from the LNG, from natural gas before you make LNG. And mercury's kind of a critical one. There are trace amounts of mercury in some natural gases, and mercury will actually cause a specific type of corrosion in aluminum equipment. So you have to, if you have mercury in your gas, you have to have a special treatment system to remove that mercury. Otherwise, not only will you foul equipment, but you'll also have stress corrosion take place in that equipment. So how is LNG made? There's really two steps to the second part of the process. So there's the pre-treatment, then there's making LNG. It's a two-part process. You kind of start cooling everything down. You cool it down and you start removing the heavier liquids that will come out. So if you have any pentanes, they will start to condense out as the temperatures get lower and lower and lower. And so you remove those from your process as you go along. You don't carry them over into your process. Otherwise, once again, they would freeze out and you'd plug up your equipment. And then you have the final stage of liquefaction is something called a flash. This is also called a Joule-Thomson valve or Joule-Thomson effect. It's also a flash. There's also a flash valve in your normal air conditioning equipment in your home. So it's no different than that. But this is the final step in making LNG. It's a process, a flash process where you take you take cold LNG that's at a high pressure, right? So you have high pressure LNG coming out of this unit here, and you let the pressure down very, very rapidly to a lower pressure, somewhere in the neighborhood of 30 or 35 psi, depending on the height of your liquid that you're depositing into, but 35 psi or so, and that's an isenthalpic reaction, which simply means that there's no change in entropy across that valve. And if you look at the enthalpy curves for any fluid, any gas, any liquid, you'll see that when you do a rapid reduction in pressure, you wind up with a very steep decrease in temperature. The other thing that you get, so nothing is free, right? It doesn't turn it completely all of it into nice cold LNG. A portion of that is turned right to vapor, and that vapor is released and becomes what's called flash gas. So a small percentage of what you actually turn into a liquid winds up being a liquid in the tank. The remainder of it becomes flash gas, and is actually in the real world is actually cycled back into this liquefaction process because it's also very cold. So it's recycled and also used as pre-cooling for your process. So just real quick, if anybody wants to ask any questions right now on some of the stuff that we covered, I'd be happy to take questions. Feel free to type something into the chat box or raise your hand. But I know I'm going kind of quick. There's a lot here, and I want to be able to get to what I'm assuming is going to be the bulk of the questions at the end. So making gas, right? So now you've got this liquefied natural gas, and it's been stored or it's been transported to an area and kept in storage where it can be used, or it's needed so it can be used. And now it's time to use it, right? So what do you have to do? You have to turn it back into a natural gas, into gas. So the easiest way to do it is just to heat it up, right? You just take that minus 260 degree LNG, put some heat into it to the point where it all vaporizes, all turns back into a gas, and then you heat that gas up to some usable ambient temperature. And how that's done is with equipment called vaporizers. And there are several styles of vaporizers, and I have a few of them listed here. An open rack vaporizer, submerged combustion vaporizer, shell and tube vaporizer, ambient vaporizer. And as I said, regardless of the equipment you use, the goal is just to drive heat into that cold liquid to turn it back into a vapor so that it can be used. Either put into a pipeline or used in some other kind of chemical process, or something like making fertilizer or whatever. But you need it in its gaseous state to actually use it, right? So the styles of vaporizers. So an ORV, an open rack vaporizer, that's a vaporizer that typically uses seawater to heat up the liquefied natural gas and turn it back into a gas. So you can see here, you've got pipes, and you've got many like fins. The LNG flows through these components here, and the seawater flows over the top and kind of rains down around these, transferring the heat from the seawater into the natural gas, turning the natural gas back into a vapor, and taking that vapor and sticking it into a pipeline or using it directly, right? So this is a very, very common style of vaporizer used to turn LNG back into a natural gas. And it's, one of the benefits of it, right, is that you're not using any source of energy to actually heat up, any additional external source of energy to actually heat up the LNG, right? You're using the temperature of seawater. So you don't have to use, natural gas. You don't have to burn natural gas and use the heat from that combustion to actually turn this natural gas back turn this LNG back into a gas, right? So seawater is one vaporization system that's used for that. And as I said, there's no additional heat source needed. It's all done with the seawater, but there's no free lunch, right? As everybody says, it takes a large amount of seawater and a large flow. So these tend to be very electrically expensive, right? The horsepower needed on the pump side to pump this seawater through these systems tends to be very large, and that's a large component of the cost of operation of these kind of units. Another kind of unit is called a submerged combustion vaporizer. Should have wrote that up here. I'm sorry, I didn't. SCV stands for submerged combustion vaporizer. And how this works, you got two different styles, but they're both the same. You see in this graphic, the burner, the flame is standing upright. In this graphic, the flame is being projected down into the water bath. But that's the gist of how these things work. You actually have the flame and its products of combustion impinging on the water. So if you had one of these things operating and you could look inside of it, right, which you can't, they're steel or concrete boxes, but if you could cut a window into that, what you would see is something that looks like a jacuzzi, water just bubbling away, lots and lots of turbulence, which makes these things very, very efficient. So you've got this burner, you use natural gas to fire these, and you send liquid LNG into a big tube bundle, right, into a pipe that's usually coiled up inside this water bath, and around the water bath are the products of combustion being pushed up through the water over this water bath. That intimate scrubbing effect you get from those bubbles transfers a huge amount of heat from the combustion process into the LNG in the tube coil, turning it into a natural back out into natural gas, or turning into its gaseous stage. So as I said, think about this, right? You've got minus 260 degrees coming into here in contact with water, right? We know water freezes at 0 Celsius, 32 degrees Fahrenheit. While this is operating, this water actually maintains a temperature of about 80 degrees Fahrenheit. So all the heat generated from the combustion, almost all the heat gets conveyed directly into the LNG, such that the water temperature really never rises to above more than 80 degrees Fahrenheit. So that's a very, very efficient way to transfer heat into the LNG using a different fuel source, using an external fuel source like natural gas. So shell and tube vaporizers. Anybody who's ever been in the process industry before has heard of a shell and tube heat exchanger. That's all these things really are. Very, very big heat exchangers. You've got a vessel. I don't have a cutaway picture of this, and I'm sorry. You have a vessel. Inside this vessel, you have small tubes that go from top to bottom. Many, many, many small tubes packed together. It's called a tube bundle. On the outside of that, you have a vessel that surrounds that tube bundle. You send liquefied natural gas in through the little tubes in the middle, and around the outside, you circulate some form of heating fluid, whether it's hot water, whether it's a glycol water mixture, or some heat exchanger fluid. And then you recircle that fluid or that water back to the heat source. You reheat it again, and you keep circulating that heat source through what's called the shell side of the exchanger, and the LNG comes in through the tubes as a liquid, gets heated up as it moves through the vaporizer, and comes out as a natural gas. Okay, so it's a very, very simple process. Then you've got ambient vaporizers, where you can actually just use air to turn the LNG back into natural gas. Works really well if you're in a warm climate. That being said, it tends to require, as you can see the size of this fan, tends to require huge fans to get enough air movement across what you see on the right here, which is a one component, one star fin, as they call it, of a vaporizer. So these big fans take ambient air and blow it across these ambient vaporizers, warming up the LNG, turning it back into a gas. Okay. Other plant components. So the pretreatment system has got, I made it real simple. I just said you take a bunch of stuff out, right? But it's got some complicated systems associated with it. There's a system, the amine system, which is used to remove CO2, so carbon dioxide, from the natural gas. There's many different. So an amine system can also dehydrate or remove water from the natural gas stream. There's also other ways to remove water with something called molecular sieve beds. That's just another way to do dehydration. And as I said earlier, if you have any mercury in your gas, it needs to be removed because it can be detrimental to any aluminum components in your systems. So there's removal, mercury removal systems in these facilities. And then on the liquefaction side, a big part, just like an air conditioner in your house has a compressor, major component in turning LNG, natural gas into LNG, is compression. So usually you have very large compressors. You have many heat exchangers, because you actually want to take that natural gas and you want to cool it down. So you have large heat exchangers, and generally the heat exchangers are all placed in one big tower, which is called a cold box. And one of the benefits of a cold box is you have all this equipment in the cold box, and you can just throw your insulation into that cold box and insulate everything. You don't have to insulate each individual pipe and elbow and each individual component. You can do it as a whole, right? That's just a more efficient way to insulate the equipment. Major component of a plant is a tank. There are several different tank designs. Single containment tank. When we say single containment, double containment, full containment, what that means is essentially how the LNG is stored in that tank. So a single containment tank means that the LNG is contained in that tank by one system, right? So in a single containment tank, you will have generally a 9% nickel steel tank that actually holds the LNG, okay? And then and then you'll have another tank built around that tank, which will be made out of carbon steel. And carbon steel is not a cryogenic steel. Carbon steel will get brittle at about -20 degrees Fahrenheit. So if you were to have a leak from the inner container, that 9% nickel steel container, and it were to leak out and you have to make contact with that outer tank, the outer tank could not support those cryogenic temperatures and could fail, could fracture and fail. So a single containment tank has the LNG in contact with the primary inner tank, and only that primary inner tank can actually contain the LNG. Let me take a step back because I jumped in a little too quick. LNG storage tanks, and you might have got this out of what I was saying, but I want to make sure it's clear. They're really just a tank inside a tank. So you have, you look at this picture here. You see this little wall here and this wall here. That actually symbolizes an inner tank. And then you have this whole structure out here, which is an outer tank. So the LNG is in contact with the inner tank. Then you've got about a 3-foot space. It's different for different designs, but on average, it's about a 3-foot space. And then you have the outer tank. And that 3-foot space is filled with insulation. Okay, so an LNG storage tank is really like nothing more than a very, very large thermos bottle. So there's no active refrigeration taking place. The only way the LNG stays cold is because the tanks are well insulated, and any heat that does translate through the tank wall into the LNG goes into vaporizing a very, very small amount of that LNG, meaning it's at its boiling point. And while it's boiling, it maintains its cold temperature. So getting back to the different styles of tanks. Single containment tanks, as I said, mean that only this inner tank has the capability of staying intact or not becoming brittle when in contact with LNG. And when you have a tank system like that, you have other structures, there's other design features of the whole facility to make it safe in the event you did have a leak, some kind of loss of containment to that tank. A double containment tank means that both the primary tank and the secondary tank can effectively contain the LNG. So if you were to have some kind of breach in the inner tank and you leaked out into the outer tank, that outer tank could still maintain the LNG without leaking it to the environment. Okay. Generally, the outer shell on double containment tanks is some kind of concrete structure. Then you have full containment tanks. The only difference between a full containment tank and a double containment tank is that the roof, that's this picture here, the roof is also concrete, a pre-stressed concrete on a full containment tank. Okay, so on a double containment tank, you could possibly breach something in the dome of the tank and have vapors liberated, right? In a full containment tank, you would not get a breach of the inner tank that would cause vapors to be liberated out of the tank. Okay, and then there's underground storage tanks, which are essentially just built predominantly underground. So they're not built above ground like this, and they have special features also associated with them. As you can imagine, any moisture in the soil could be a problem as you get heat migrating into the LNG through the tank wall. You actually cool down the earth around that tank, and so there are special precautions and special design features in a tank of this design. LNG tanks have gauging systems where you can measure several things. You can measure the level. So LTD gauging stands for level, temperature, and density. As I mentioned to you earlier, as LNG sits inside a storage tank, it actually changes in its composition, and what you actually get is a change in composition all through the height of the LNG. So I'm going to use the words heavier and lighter here. So the heavier LNG will segregate itself over time and be closer to the bottom of the tank, and the lighter LNG will wind up floating higher in the tank. And with the LTD gauge, you can actually get a density profile through your LNG, and that density profile actually will match changing temperatures through that tank. So heavier LNG is warmer than lighter LNG, so you'll have warmer temperatures at the bottom and cooler temperatures at top. We're not talking about huge differences here. We're talking about a couple of degrees per reading at most. So it's not we're not talking about minus 260 on top and 0 degrees someplace at the bottom. It's not that drastic. But in the storage of LNG, those slight temperature differences matter for other reasons. The tanks all have pressure relief valves on them, and also vacuum relief valves. So as you can imagine, when you need LNG, you take it out of the tank. As you take it out of the tank, you can actually take it out too quickly, where you can cause a vacuum inside the tank, And if that were to happen, you could actually collapse the tank. That's not unique to LNG tanks. That's unique to all storage tanks. So LNG tanks have vacuum breakers built into them, okay, or attached to them. Also, there are overfill devices on an LNG tank. If you were to put too much liquid into this inner tank before it flows over the top into the space between the two tanks and could possibly cause a fracture on a single containment tank, there's actually a system that allows the LNG to pass through a piping system, let's call it, and deposit LNG out into the impoundment area. So there could be a visual indication that that you've overfilled the tank. That's not normal. It's not a normal operation. So I don't want to make you think it is, but it's one of the safety features built into LNG tanks. Another component of a plant that turns gas into a liquid and exports it, or that maybe you have a facility that does not export gas and just imports gas and doesn't make their own LNG, is a shipping berth. Sorry, you saw that. Whoops. Is a berth, right? There are many different size LNG ships, and you can see this, largest ship here, the QMax ship, can hold up to 266,000 cubic meters of natural gas. So I don't have a comparison for you for the Philippines, but in the United States, in the New England area, which is the northeast region of the U.S., where it gets cold, very cold in the wintertime, about 160,000 cubic meters can supply all of the New England region in the United States on one of the coldest days. So that gives you some idea as to how much capacity there is in these ships, right? Some of the components, of a berth. A berth is designed so that the ship can be moored, safely. And there are simulators. The most common one is called Optimor. It's a simulating system that simulates the actual berthing of a ship, given the tides in the region, given the currents in the region, given the composition of the dock, the position of the bollards and such. There's automatic tensioning systems. So when you have a ship attached to the dock, the tides go up and the tides go down, and how tight that ship is held to the dock needs to be adjusted. And so there are actually tensioning systems used on these ships to maintain the proper tension on those lines while the ship is at the dock. And that's important not just for tides, but because you can imagine if you have a ship full of LNG and you start removing LNG from that ship could actually rise a little bit in the water. There are other ways that's controlled on these ships, but that's one thing that can happen and cause tensions on lines, and vice versa. If you have an empty ship and you start filling it with LNG, that ship's going to get heavier and get lower in the water, and you could lose tension on your mooring lines. As I said, that's offloading and loading a ship. There are other mechanisms that are used to maintain the height of the ship in the water. So that's, this mooring and tensioning is not the major way of maintaining that, but it's useful in that. Mooring systems really are effective for when tides change. As an LNG ship is berthing at a dock, there are laser systems that actually measure the speed and the angle that the ship comes in approaching the dock, right? And as you can see, these are huge ships. A ship that's 100 and the small one up here, 125,000, 150,000 cubic meters is almost the size of a standard U.S. aircraft carrier. As these ships are being berthed, are being brought into the dock. If they're brought in too fast or at the wrong angle, they can be severely damaged, and they can do severe damage to the docks, right? So these systems here are critical in assuring safe operation. And down here is an example, or is an illustration of a U.S. United States football field. So it gives you scale, idea of scale between a football field and these ships. Plant components continued at the dock. You need to get the LNG off the ship once you get the ship to dock. What you see here are what's simply called unloading arms. They connect to a manifold on the ship. Inside the ship, there are tanks with the LNG in those tanks. There are pumps in those tanks. The pumps pump the LNG out into these unloading arms, which are connected to a piping system and bring that LNG to the plant, back into storage. One of the safety systems on these arms are something called PERCs, which stand for Powered Emergency Release Couplings. So if you were to have an incident or severe movement for some reason of the ship in the dock, these connections can automatically release, and the ship can be released from the docking facility. Also, there's a system called an umbilical connection, which is connected to the ship and allows the plant that's receiving the LNG to communicate with the ship. And when I say communicate, I mean through control systems. So if you were to have an emergency shutdown occur, or a sudden change in pressures or flows occur that could be detrimental to the plant could shut down the ship transfer, and vice versa. If you had an incident on the ship where something occurred, and the plant wanted to protect itself, it could shut itself. The control system could isolate itself from the ship, and the ship can isolate itself also from the plant. Fire and gas detection system. So we talked about some of the design points in an LNG facility, but a very, very, very major component is the other control systems. And there's many hazards in any plant, but in LNG plants, you have your major hazard is fire. When you build a facility, there's a specific kind of study that's done to determine where those hazards are, where the most likely places for hazards to occur, and which components should be installed in the facility to be able to detect those hazards and do various things, whether it be shut equipment down or notify people and say, hey, I got a situation over here. I want somebody to take a look at it, and an alarm will go off, and notify an operator that maybe there's something they should look at. Major part of the design of an LNG facility are the fire and gas detection systems. Also in LNG facilities, there's the big red button. They're located many places, strategically located throughout the facility, plus also in control rooms, which allow anybody basically to push that button and completely shut down the LNG operations, right? So completely shut the plant down and put it in a safe state. So an ESD system would close all the valves, make everything safe, in case somebody, in case there was some kind of situation, somebody thought there could be a hazard. There's also pressure relief devices located throughout the whole facility, where you protect piping and equipment from surges in pressure. One of the ways you can get a surge in pressure, you can imagine, as we said, LNG is liquefied natural gas, minus 260 degrees. It's got a 600 to 1 expansion ratio. Well, if you have a pipe and you close the valves and you don't let that LNG flow anyplace, and it starts to warm up, well, it'll want to go back to 600 times its volume. And what will happen is you will cause increases of pressure in that section of pipe. And through those, throughout the design of the facility, you have pressure relief devices located to relieve those conditions if that were to happen. Okay. Your control systems include temperature control and flow control to regulate how the systems work, whether they're producing LNG or whether they're vaporizing LNG. The flows and temperatures are critical to the operations, and they're monitored and controlled by a control system. Codes and standards, basic introduction here. There are Nfpa 59A is the standard production of LNG, and it's been around for a very, very long time. First published in 1967, and it's actively updated as the industry changes, as technology changes, as more is learned about about safety. If any lessons learned are out there, it's updated on about every 2 year schedule. It's been widely adopted throughout the world as the standard used to build and operate LNG facilities. It's sections within 59A actually are built on some parts of the U.S. federal regulation, and this is that code right there. 49 CFR Part 193 is the U.S. LNG regulation, and within this document, you'll actually find some requirements that mimic 59A. That mimic 49 CFR 193. I'm sorry. And you will also find within 49 CFR 193 many parts of 59A directly referenced. Okay, it's a very, very well used, well designed standard. And then there's also a well-known, well-used European standard. It's EN 1473 for the design of LNG facilities for onshore LNG facilities, and it is more of a risk-based design for LNG facilities. So NFPA 59A and the U.S. regulations are very prescriptive in how you design an LNG facility. 59A does have NFPA 59A does have a whole section on risk-based design, but the European standards have always been risk-based design standards, and it's like a completely different strategy on designing a facility than a prescriptive strategy, which is prescriptive strategy has been the U.S. strategy forever since the regulations were written. So I don't know if Kevin is around, but sorry, Kajin is around, but Kajin's with GTI, and you got me on the right there. You have my phone number, my email address. You have Kajin's numbers there. After this presentation, any questions that come up that you might not have thought about during the presentation, feel free to contact either one of us, and we'll be able to get you information or find something out for you if we don't know it.
All right. Thank you very much, Mr. Scaraji, for that informative presentation. We will now be having our Q&A. We'll be reading the questions posted in the chat box, and we'll also open the floor to participants who want to ask questions directly to Mr. Scaraji. Just please press the raise hand icon. So let's go first to the questions in the chat box. Here we have a question from Sarah Blanford. Are you capturing elements like mercury for sale, or do they get reused in some way?
So generally, no. When it comes to components like mercury, they're just removed, and those the amounts of mercury in natural gas are really, really, really small, and it would take huge amounts of natural gas to make any significant quantity of mercury. The systems that are used to remove mercury are actually sacrificial bed systems. So the mercury collects in those beds, and then those beds get disposed of. So there's no methods for collecting something like mercury. Now, in certain parts of the world, many parts of the world, where you have markets for other components like propane and butane. Some cases, pentanes, depending on what the industries are in that area. They will be removed from the LNG stream, from the natural gas stream, before they become part of the LNG and be sold separately. Once again, those are only really in areas where there are markets for those. And those areas also have to have a premium to what the LNG would cost if you did not remove those components from the LNG, right? Because LNG is sold on an energy basis. So when you remove some of those heavier components, you're removing some of the higher BTU value components, and you're making an LNG that has a lower BTU value. So there's a whole kind of financial analysis around that, as well as whether there's a local market for it.
All right, thank you. We also have here a question from Cerces Fernandez. Can offshore unloading be done using an Amazon pipe?
Can offshore loading be done? I am not familiar with the term Amazon pipe, so I don't know what that is. Sorry, sorry about that. But offloading being done offshore is, I'm assuming you mean of the liquefied natural gas, has not been done that I know of, simply because of the cryogenic temperatures and the types of insulation you would need on piping systems to transfer the LNG. There are facilities that have very, very long tunnels that connect the offshore berth to land, and within those tunnels they'll have LNG pipes, but no direct pipes on the seabed, so to speak, that I know of.
I think Cerces Fernandez raised his or her hand earlier.
Yes, I'm sorry, I didn't see that.
Yes, sir. Yes, you've answered my question. It's typically what I was asking is if the ship is not really docked or not properly or not moored at the dock, if there's a system wherein it's kind of in the middle in an anchorage area, and what systems can be used, and you basically answered it. Basically you said that there could be an offshore facility where pipes that are cryogenically controlled can be laid out to the regasification facility. But for the using of Amazon pipes or those kinds of devices is not practical or advisable. So it can keep the LNG in liquid form. So thank you very much for your answer, sir.
You're welcome. Maybe is this another part of this answer could be if you did have a ship offshore that for some reason was not able to get into the dock for maybe a mechanical reason or some other reason, occurring at the facility, and a different ship would be able to get to the dock where this one that has the LNG couldn't. There is a way to do a ship-to-ship transfer. So there are ways to transfer LNG from one floating ship to another floating ship, and then have that second floating ship deliver the LNG to someplace where the first one might not have been able to go. I don't know if that helps at all. That's just another thought in oceanside transfers.
Okay, so let's move on to the next question. We have a question from the director of DOE OIMB, Director Rino Abad. He asked, what are the major standards applicable to a regasification terminal from jetty, unloading arm, receiving pipeline to the storage tank, vaporizer, and send out pipeline?
So the as I mentioned earlier, from an international perspective, most widely used standard is NFPA 59A, and that covers all aspects of an LNG facility, all systems from dock right through to discharging gas from vaporizers into piping. It also includes design of liquefaction facilities where you have many different components that are used for liquefaction. So you'll have ethylene and isobutane, isopentane, all kinds of refrigerant components, liquefied nitrogen, all those components. The design of systems for those components will all be incorporated, are all incorporated into NFPA 59A. From a U.S. perspective, I don't know if that helps at all. From a U.S. perspective, there's the standard, there's the U.S. regulation, which is 49 CFR 193, which also covers every aspect of design of an LNG, of all LNG facility components. Then, as far as the specific design of components, within the LNG facility, so for example, pressure vessels, piping design, fire protection system design, those standards will all reference appropriate standards. So whether it be ASME B313, which is process piping standard, which referenced in 59A for all those pressure piping and pressure components, and it's also referenced in the U.S. standard 193. And then you'll have usually for all the fire components, the fire systems, NFPA, National Vibration Association standard, will be referenced for those. I hope I answered your question.
All right, thank you. There's a lot of questions coming in. So let's move on to the next question from Mr. Eric Cruz of GPDP. Regarding berthing of LNG ships, are automatic mooring systems like Optimoor always required? There's actually two questions. And the other question is, will traditional mooring system like tension cables fixed to the bollards not work for LNG ships?
So the Optimoor is a computer simulation program to determine how to moor ships given all the different variables of the specific port. There are other systems out there that can be used for modeling, but Optimoor is by far the most commonly one used out there. If you're designing a facility and you're going to moor a ship at that facility, you're going to be using some kind of simulation software to model what the requirements would be to safely moor that facility. So whether it's Optimoor or something else for simulations, you're going to be using some kind of simulation program. The automatic tensioning systems, they work on LNG ships, and they're used quite frequently. There are also quick release mooring connections on LNG ships. So if you were to have overtension a line, the line would automatically be remove itself, would uncouple from the bollard. But non-automatic tensioning systems are still in use particularly at older facilities, they just require more diligence, let's say, by the crew and by people doing rounds at the facility and monitoring those things.
Mr. Eric Cruz is raising his hand. Mr. Eric. I think you're mute, sir. Nakamute po.
Thank you. Thank you for your reply. What I actually intended to ask was about the thresholds of ship motion that are permitted for the LNG ship. And I think the Optimer program will make sure that these motions are constrained to within the limits of the to which the LNG ship will need. So, in other words, if the threshold of motions can be restrained to certain values that are permitted by the LNG ship, will this do, like, well, in this country, these automatic mooring systems are not common. We use the traditional mooring system like tension cables fixed to the dock bollards. And,
Yes.
yeah. And as long as we can control the threshold of ship motions, will this mooring systems do already for the LNG ships?
Yeah, so that's a very good question. Particularly the older, it's something that particularly the older facilities run into, in that ships have progressed through the years, and a facility that was built in, let's say, 1971 may not have had the capability or let's say the resources even to progress as quickly as the ships have. And those facilities can still safely moor ships. What happens with traditional mooring systems? What happens is you do the kind of upgrades that you can do, like the laser positioning systems and such, to be sure that the angle of approach and the speed the ship is being brought in at are appropriate and won't cause damage to the ship or the facility. But the Optimer, that's one of the places Optimer comes in. You take your existing facility and you simulate your existing facility with all the positions of all your bollards. You incorporate the tidal changes, the currents of your particular berth, the depth of your berth and such, and you simulate what needs to be done to safely moor that ship within the envelope, the unloading envelope, right? So those unloading arms that I talked about real briefly, they do have some ability for lateral movement as well as vertical movement. And so you have to keep the ship movement to within the envelope of those unloading arms. With the Optimer system, you can take your existing facility, simulate a specific ship, because it is ship specific, a specific ship at your facility to determine whether or not there is a compatibility, the ship is compatible with your terminal. So there's a whole process of vetting ships to come into docks. And there's a ship-to-shore compatibility analysis that's done, which includes the Optimer system or some system like it. But Optimer is by far the most widely recognized.
Thank you.
All right, thank you. So our next question is from Mr. Don Honor B. Jacob. What government agencies conduct inspection of LNG or natural gas facilities, and frequency of inspection? Do you have inspection manuals that we can copy?
So I can give you a general perspective, and then I can give you a very, very specific U.S. perspective. I'm not sure if the U.S. perspective is helpful, but I'll give you that. Generally, this is the general perspective, obviously. Generally, there'll be some form of Coast Guard inspections, Coast Guard technical reviews, and marine side safety reviews, right? That kind of stuff will be generally done through some kind of Coast Guard type agency. The facility design will be done through so in the U.S. that's done through the Federal Energy Regulatory Commission. So a similar regulating body in a different country would most likely have a responsibility of reviewing designs and proposals for LNG facilities to make sure that they're designed in the public interest. right? That they're safe, can be operated safely. And in the case of critical energy infrastructure, where they're going to be relied on, for national security, let's say, if you install this and you start using it, it becomes a major component of your economy, of your national security. One of the things that an agency like that would do is be sure that the design is reliable as well as safe. Then you'll have either the same agency or a sister agency who will do the actual inspections. I'm going to say like the real-time, ongoing inspections of the facility to be sure that they're in compliance with their procedures, with the regulations. The design has not substantially changed, so the company didn't decide to install an additional liquefaction system without getting approvals. They'll be involved in those inspections for those things, as well as a huge part of LNG operations is training. They'll be involved in personnel training, training records, reviews, and such. Also, in the U.S., you have a company, an agency like OSHA, that gets involved in basically all aspects of plant safety from construction through to operation. Although in the U.S., OSHA has some limits on what it's involved in the on the LNG side through like memorandums of understanding between itself and another government agency, being the Department of Transportation in the United States. So that's the general perspective. The more specific perspective that I can give you is the U.S. one, where, as I said, the Federal Energy Regulatory Commission, FERC, does basically an evaluation as to whether or not the facility is needed, or I should say you provide an evaluation to them based on the requirements of what that evaluation looks like. It's an EIS, environmental investigation, essentially, where you talk about all the different options and effects on the environment from your proposed facility. And then if you get a positive EIS, then you submit your design to them, and they evaluate your design for safety and for compliance with regulations. And there's generally a big back and forth between FERC and the project, or the people trying to build the company trying to build the facility, so that everybody's on the same page. Everybody understands, what the intent is of the facility and how it's going to operate. Then you've got another agency in the U.S. It's part of the Department of Transportation, which is PHMSA. And that regulation I talked about, the 49 CFR 193, is actually a DOT regulation that covers all aspects of LNG, from design through to training to operations, all the way through to things such as control of corrosion, right, in your facility. So very detailed, prescriptive regulation. So you have those three agencies, and if you're a waterfront facility, then you have the U.S. Coast Guard that also has requirements for its own design, and there's also the U.S. Coast Guard has its own federal regulation. So I talked about 49 CFR 193. There's also 33 CFR 127, which is another federal regulation in the U.S., specifically a Coast Guard regulation on LNG. For LNG facilities. So you have all these different agencies that are involved in the design side, and if you're exporting LNG, you have to get permits from the Department of Energy. That's not a design thing; that's a commercial thing. But that's another piece of the puzzle. With all those agencies on the U.S. side, FERC inspects facilities physically no less than once every 2 years. And the Ferc inspection is an inspection to be sure that the facility is still in compliance with what they originally approved when they approved the building of the facility. So it's actually a design review of the facility. So every 2 years, that's done. Many facilities in what I'll call high visibility areas, with high population densities and such, they'll get that FERC review annually, so once every year. The DOT PHMSA inspection is an inspection that's done of facilities to the regulation. So the regulation requires you to have certain records, have certain procedures in place, has requirements for those procedures, has requirements for reporting of different conditions that occur in your facility, whether it be a safety-related condition, or whether it be a failure, some sort of a failure of equipment over a certain value. There's all these kind of reporting requirements in that footnote CFR 183. And DOT PHMSA generally visits facilities annually. Sometimes they will not. Sometimes they'll skip a year. It's probably just based on their workload. It's not based on whether or not they think a facility is safe or unsafe. The PHMSA has the ability to issue enforcement actions against a facility if they find it's not in compliance, or they believe it's not in compliance with the regulations, or if they believe the facility, the company or the facility, operated, blatantly in violation of the regulations, right? There are different levels of enforcement action, from something as the lowest form being a warning letter, the most severe form being a directive, you shall do this kind of thing, and theoretically they can actually take over operations of the facility if they wanted to, right? That's the most extreme level of enforcement action. In the middle, there's actions called notices of amendment, where they require you to amend your procedures, and violations. Violations can have monetary penalties attached to them in excess of $1 million per event that occurs, that they find at the facility. I hope I didn't give you too much on the U.S. stuff. Unfortunately, that's my that's what I know the most about. But in general, that's the way it works. I'm sorry, I missed the U.S. Coast Guard. And the U.S. Coast Guard also does inspections. They do annual inspections, and they tend to do unannounced spot inspections, sometimes as frequently as monthly. And it could be, the U.S. Coast Guard guys and gals. They're it's a military organization, and they're 24/7. So you could get somebody showing up at your facility at 3 o'clock in the morning to do an inspection. That's not out of the ordinary. It's not necessarily common, but it's happened before. So I hope I gave you a good perspective on. I hope I answered your question in a way that's helpful.
All right, thanks for that thorough explanation, Mr. Scarachi. In the interest of time, we can accommodate only 2 more questions. So we will have Mr. Carl Regudo's question, and to entertain questions from the other agencies, Engineer AC Gallardo Jr.'s question. So Carl Regudo from GPDP would like to clarify, Nfpa 59A is the basis which the CFR adopts. That is, if Nfpa issues changes, CFR adjusts accordingly. Or are there cases where CFR adopts changes, which in turn the Nfpa 59A revises in newer versions?
So that's a great question. In the U.S., the CFR is the driving document. So it is the lead document. if there's a conflict between, so the CFR does not incorporate NFPA 59A in whole. It incorporates portions of the 59A document into it. Excuse me. So it doesn't say, you know, build your facility to 59A and it's acceptable. It has its own sets of requirements, and then in certain areas it says, okay, for fire systems, use Chapter 9 in 59A, and 59A, you know, every 2 years progresses, and a new issue comes out. The CFR is only changed by, you know, by promulgating regulation, you know, by actual government action. So so the CFR is not updated as frequently by any means as the standard is, as the 59A standard is. So the CFR actually references a specific version of the 59A standard for the sections that it references 59A within itself. So currently, NFPA, the newest version of the NFPA 59A is the 2019 version, 2019 version of 59A. The federal regulation references, for the most part, the 2001 version of NFPA 59A. And for a very, very small subsection of the references, all having to do with seismic design, it references the 2008 version of NFPA 59A. As a regulation, as law in the U.S., the CFR, my understanding is the CFR cannot reference a standard and say use the latest version of this standard. They have to actually reference a specific version of a standard, which really leads to a lot of design issues for LNG facilities. So, for example, you know, ASME, boiler and pressure vessel code, widely used document, you know, throughout the world. The version referenced in 49 CFR 193 is the 1996 version. So, you know, you do wind up with very, very strange situations within the U.S. regulation. I hope I answered your question.
All right, thank you. So for our last question from Engineer AC Gallardo Jr. of Philippine Ports Authority. Philippines' power energy is more than supplied by coal power plant. May we know the stand of the U.S. government of the continued use of this coal power plant in your country because of effect to health? Is LNG more advantageous to coal power plant?
So I don't wear the right kind of hat to speak for the United States. So I can't really you know speak to the whole country. You know, that being said, as the whole world now is driving towards, you know, decarbonizing, the United States seems to have been these days getting more and more on board with the rest of the world on that, right? And when it comes to fuels, the cleanest burning fossil fuel we have right now is natural gas. And so you know, the global warming issues, air quality issues, issues associated with you know, with actually extracting you know, coal from the earth, all the environmental issues associated with that are all generally greater than the environmental issues associated with natural gas. So you know, if when you talk about, you know, global warming, right, it's a fossil fuel issue. So natural gas is still a fossil fuel. So it's not necessarily the solution to global warming. It's really the cleanest solution we have now. So it's been called a bridge to renewables. right? So it's the way to get from larger, heavier, denser, less environmentally friendly energy sources, of which coal, generally is in that category, to in the end, renewables. And there's also schools of thought out there that say 100% renewables is really pie in the sky, right? Because we need to have some kind of battery technology to be able to store that energy when when the wind is not blowing, when the sun is not shining, that kind of thing. And that technology, although it's advancing, it is not there yet. So during those times when you don't have enough renewables to supply energy to the system, the cleanest way to do that with a fossil fuel is with natural gas, right? So there may always be a place for natural gas and LNG in the overall energy infrastructure of all nations. That said, there is certainly a drive away from the more complex hydrocarbons to the lighter hydrocarbons, and then away from hydrocarbons completely and into renewables.
All right. Thank you once again, Mr. Scaraji. And thank you all for your questions. So for those whose questions have not been answered, we will be taking note of them and we'll send you our expert's response after the training. And a quick reminder for those who haven't answered the attendance form yet, a link is posted in the chat box. So please don't forget to answer our attendance form and be careful on typing your full name, as we will use these details to prepare your training certificates. So before we conclude the training, may we please request everyone to open their cameras for a quick group photo. Let's all flash our beautiful smiles. All right, so everyone ready? Say cheese in 3, 2, 1. Smile. Again, 3, 2, 1, smile. 3, 2, 1, smile. Last 3, 2, 1, smile. All right, so thank you everyone. That concludes our session. We want to thank Ms. Karaji for sharing with us his time and expertise today. We will have him again tomorrow for the Advanced LNG course. So that's a reminder to everyone. Our second course is tomorrow, same time at 10 a.m. Philippine time. We hope to see all of you again. Thank you very much, everyone, and see you all tomorrow. Have a nice day and stay safe.
Thank you.
Thank you.
Thank you.
Thank you for.
Thank you.
Thank you.
Thank you.
Thank you po.
Thank you, everyone.
Sorry.
Thank you.